Search strategy. This is the second step. We have a search space. It is designed, handcrafted by you. And in that search space, this, I repeat, this is like a function. The input is some parameters, number of filters, the architectural design. And with different parameters, it will provide you an architecture A, just like this. And the search strategy will designate which parameters will come at the next iteration. So what is the iteration? You start with a search space. The search strategy gets an estimation of the performance, and it will know this architecture has this performance. Then, by judging at this performance, if it is too high or too low, it will make a change. If it is too low, it's going to make a dramatic change, maybe, depending on the strategy. If it is very good, it will make a slight change to find some little improvements. Or it will change the parameters of the search space so that it gets new architecture. So how does it change it? The search strategy details how to explore the search space, which is often exponentially large or even unbounded. I mean, there could be infinite possibilities depending on the handcrafted architecture, the structure of the search space. I shouldn't use the architecture because architecture is like the output that this search space provides. The mechanism inside the search space, I should maybe mention always using the word structure. So the structure, the mechanism of the search space will provide an architecture. So the search strategy encompasses the classical exploration-exploitation trade-off. Since, on one hand, well, you want to explore every possibility, but you want to find a well-performing architecture very quickly. If you explore many things, it will be difficult for you to find some architecture working your way quickly, right? So this is a problem of optimization, guys. If you're doing a trade-off, you're optimizing something. You're optimizing time, you're optimizing the training, the hardware you're using to do the training. You're optimizing anything. You're optimizing the number of layers that you're going to use because maybe you're going to embed this in a system and you don't want it to have thousands of layers. Maybe you say, I'm going to have 10 layers. So these bounds, these constraints are actually a title, subjects under the title of optimization. So many different search strategies can be used to explore this search space of neural architectures, this guy. But namely, they could be random search, Bayesian optimization, evolutionary methods, reinforcement learning, gradient-based methods, neuroevolutionary techniques, evolutionary programming, genetics algorithms. All these titles I've just discussed now are actually titles of optimization. And guys, maybe I should tell you this, at this point on, just like I said a couple videos earlier, if you want to continue on this field, you need to get a proper optimization course. Without an optimization course, it will be very difficult for you to understand it. And actually, we are going to discuss reinforcement learning a little. I'm going to introduce it to you again. But maybe it's better you get a machine learning course as well. Because before convolutional neural networks and deep learning, there was optimization and machine learning. Many methods from those fields are inherited in this search strategy thing. So in the following slides that I'm going to talk about, we'll be talking about some basic machine learning techniques and optimization techniques. Maybe you'll be hearing them for the first time. It's okay. I'm introducing this subject to you, but if you want to work on this field, in the field of deep learning actually, because this is the future of deep learning, I strongly recommend you guys, to get an optimization course. Otherwise, it will be very difficult to just follow the state-of-the-art improvements in the field. The field will be moving to this subject very soon. It has already moved actually. Okay, let's continue. Let's start with random search. You have a search space. You're randomly searching. Yeah, you can do that. I mean, there are optimization. This is a type of optimization actually. You're randomly searching. It sounds a bit stupid, but it has its usages, guys. This is the most simple and most unreliable way to search because you will definitely get lost. When you're looking for something, you're trying to find your way in a city, for example. Well, you get some clues. you look at you look at your map, or you ask people. If you have no idea where you're going to go, if you just randomly walk all the city, you won't be able to find your way, right? But there might be cases that you need to use random search. So at this model, you make at each iteration, you make a random change in the architecture. So without taking into consideration how previous trials performed. Because you search something, you get a performance estimation, and you decide your next step accordingly. If you don't, you make a random search. It doesn't matter in which order you do it, but this time you'll get lost. For some search spaces which are highly diverse and non-convex is a discussion of optimization, guys. Convex architectures in optimization are easy to converge to find the optimum points, and this is a technical term and you will learn when you get an optimization course. I'm not going to go into the detail of it. In those cases where the dynamic structure of the search space is so diverse, it's difficult to find your way, you may use random search, maybe to make a preliminary search. You'll make a preliminary search to find an area in your search space which is nice, and in that area maybe you're going to make a more sophisticated search. So it could be used as a preliminary search technique. So it's not totally useless. But it's generally a low limit benchmark. I mean, why do we have this random search? Well, you're using random search because it's so diverse, because any other non-random search strategy is either too expensive or somehow not compatible. It won't converge. In those cases, you may use it as a preliminary search maybe, but usually random search is used as a benchmark for other optimization algorithms. It is trying to say, I've tried optimizing it with genetics algorithm and it is working this much better than random search. Because if your optimization algorithm is not working better than random search, you are doing a terrible job. You are doing something wrong. You should correct it. Random search is like the low limit benchmark. Okay, so we still need it. You still need random search to show that your optimization strategy, your search strategy, is working fine. It's making sense. Very good. Now we continue with other ones. From now on, I'm going to each slide, I'm going to give some information about some search strategies, some titles. Guys, these will be just titles. I mean, this course is not the place to teach you Bayesian optimization or reinforcement learning or genetics algorithms. You'll need other courses, but I must introduce them to you. This is the way it is done. Then another search strategy will be Bayesian optimization. Bayesian optimization is based on the probabilistic approach of the Bayes formula. Bayes formula is having a prior probability to find a posterior probability. It is like knowing an information about something and using that prior information about something, trying to make a better guess out of it, combining different information, different prior probabilities to get a better information, to get a better estimate, to make a better decision. So Bayesian networks, Bayesian optimization, this Bayesian probability formula, they're all based on this idea, prior to posterior probability. So this is a sequential design strategy. What is a sequential design strategy? Is where the sample size is not fixed in advance. Instead, you collect data and you sample data in accordance with a predefined stopping rule. So how do we use this? If you just want to do Bayesian optimization, there's a nice article, guys, again in Towards Data Science. In natural language processing, Bayesian optimization and Bayesian-based techniques are widely used. So if you're going to do natural language processing, sequence modeling, or dealing with natural languages, understanding language using recurrent neural networks, I strongly recommend you to get these guys. So the important thing about this technique is it doesn't require derivatives, because if you've taken my previous semester's course, while we were working on training, we've used the derivatives to find better weights. Derivatives are like looking for a direction. This guy, the Bayesian strategy, is used when you cannot get derivatives. And it's very difficult to get derivatives, guys, because you have a search space, You need the derivative of the performance with respect to the parameters of the search space. Very complex problem, because this is not some mathematical function which is analytically defined. It doesn't have an explicit function. It is very difficult to estimate the derivatives so that you could follow the way of the derivatives, just like most optimization algorithms do. In these cases, Bayes-Jones optimization is widely used, guys. This is all information I'm going to provide about Bayes-Jones optimization. If you need more, you'll have to just take new graduate courses, other graduate courses, and work on the field yourself. And another one is reinforcement learning, and let's continue this on the next video.